Welcome back for another deep dive. This time we're going to be exploring something you use every single day, even if you don't realize it.
Data systems.
That's right. We're going behind the scenes of data systems, those amazing systems that power pretty much every app and website you use.
It's pretty remarkable how much data is constantly being stored and processed, isn't it?
It is. And we've got a ton of sources here, articles, research papers, all sorts of stuff.
And I'm here to help make sense of it all and guide us through this fascinating world of data systems.
I think it's going to be a fun one. So let's kick things off with the basics.
Sounds good.
When we talk about data systems, what are we actually talking about, and what makes a good data system?
Well, at the core, a data system is essentially anything that helps us store and process information digitally. Think of databases, message queues, caches, all that jazz.
Right. Like they all just store data, right?
Well, yes, but not all data systems are created equal. There are three key characteristics that developers focus on: reliability, scalability, and maintainability.
Okay, let's break those down one by one. First up, reliability. Why is that so important?
Imagine losing all your photos or financial records because of a system crash. That's what we want to avoid. A reliable data system minimizes downtime and ensures data integrity. It's about making sure your data is always there when you need it and that it's accurate and trustworthy.
Makes perfect sense. You definitely don't want your data disappearing or getting corrupted. What about scalability? Is that about handling massive amounts of data, like all those cat videos online?
That's definitely part of it. Scalability is all about handling growth, both in terms of the amount of data stored and the number of users accessing it.
Okay, so as more people use a service or as more data is generated, the system needs to be able to keep up.
Precisely. And we need systems that can handle different types of processing, like batch processing for analyzing huge data sets.
So like those big data analyses we hear about.
Exactly. And then you have online systems that need to respond quickly to user requests, like when you're searching on Google or making a purchase online.
Right. It's all about speed in those cases. So different tasks require different approaches to scaling.
Got it. Now, what about maintainability? Why is that so important?
Well, think about it. You wouldn't want to buy a fancy new gadget that becomes outdated in a year, right? You'd want something that can be upgraded and adapted over time.
True. Like it's better to have something that's built to last and can be easily improved upon.
Exactly. And the same applies to data systems. Maintainability is about designing systems that are easy to understand, modify, and keep running smoothly for years to come.
You mentioned maintainability. It's like when you buy a fancy new gadget and a year later, it's already outdated. You want your data system to be more like a classic car, well built and easy to upgrade over time.
Exactly. You need to be able to keep it running smoothly, fix any issues that arise, and adapt it as your needs change. Think about a company like Netflix. They have millions of users streaming movies at the same time.
Oh, yeah. They definitely can't afford to have their systems crash. Right. They need to be reliable and scalable, for sure. But they also need to be able to constantly adapt to new technologies and changes in user behavior.
And I'm guessing that involves a lot of different tools and technologies working together behind the scenes.
Absolutely. They use a mix of databases, caches, and all sorts of other components, all working together seamlessly to deliver that smooth streaming experience.
Wow, so it's a whole ecosystem behind the scenes.
It is. And that brings us to the concept of a composite data system. This is where you combine multiple tools, like databases, caches, and search indexes, to create a new specialized system.
So kind of like building with Legos, you pick and choose the best pieces for the job and put them together.
That's a great analogy. And to make it all work, you need a clear and well-defined API. That's the interface that applications use to interact with the system.
So the API is like the control panel for the whole system, making it easy for applications to access the functionality without having to know all the messy details underneath.
Exactly. It hides the complexity from the users and allows them to focus on what they need to do. But it's important to remember that there's still a lot of responsibility on the developers who build these systems.
Right, because they need to make sure all these different parts work together seamlessly.
Exactly. They need to ensure that the different components are configured correctly, that they communicate effectively, and that the data remains consistent across the entire system, like ensuring cache consistency, for example.
Cache consistency, what's that?
It's about making sure that the data stored in the cache, which is basically a fast temporary storage area, is always up to date with the main database.
Ah, so you don't accidentally show someone outdated information because the cache hasn't been updated.
Precisely. That's just one example of the many things developers need to consider when building these complex data systems.
Okay, so we've got the fundamentals down. Reliability, scalability, maintainability. Now, let's talk about how data is actually organized and accessed within these systems. I've always been a bit confused by the terms data models and query languages. Can you break those down for us?
Sure. Think of data models like blueprints for how data is structured and organized. The most common one is the relational model, which uses tables with rows and columns, kind of like a spreadsheet.
Oh, yeah, the classic spreadsheet, rows and columns, I get it.
It's been the dominant model for decades, and it's widely used for a reason. It's structured, organized, and we have a powerful query language called SQL to work with it.
SQL, I've definitely heard of that. But I also keep hearing about these NoSQL databases. Are they totally different from relational databases?
They address different needs. Think about data that doesn't fit neatly into those rows and columns, like comments and likes on a social media post. It's all jumbled together, right?
Yeah, it's not as structured as, say, a list of customers in a database.
Right. That's where NoSQL databases come in. They use different models, like the document model, where data is stored in these flexible, self-contained documents, kind of like JSON objects.
Okay, so we have relational databases with their neat tables, and then we have document databases for more free-form data. What are the pros and cons of each?
Well, relational databases are great for structured data. Think of things like customer records, financial transactions, or product catalogs.
Things that fit nicely into rows and columns.
Exactly. And SQL is very powerful for querying and manipulating that data. But what happens when you have data that doesn't fit neatly into rows and columns?
Okay, so we have relational databases with their neat tables. But what happens when you have data that doesn't fit neatly into rows and columns, like, say, all the comments and likes on a social media post?
That's where document databases like MongoDB shine. They store data in flexible JSON-like documents, perfect for those nested structures. It's like storing an entire customer profile in a self-contained document rather than spreading it across multiple tables.
So it's all about choosing the right tool for the job.
Yeah.
When would you opt for a document model over the traditional relational one?
When your data naturally fits into a document-like structure, think of embedded comments, user profiles, or product catalogs. It simplifies things, especially when loading large chunks of related information. However, performing joins combining data from multiple tables based on a common field can be more challenging with document databases.
So there are trade-offs, just like you mentioned earlier. Now, I've also heard whispers about other models like MapReduce and graph databases. What's the deal with those?
Think of MapReduce as a powerhouse for processing massive data sets. Popularized by Google and used in systems like Hadoop, it's a programming model that breaks down complex tasks into smaller, parallel operations. It's all about tackling those enormous data sets efficiently.
Okay, that makes sense for big data scenarios. And what about graph data models?
Graphs excel at representing interconnected data, like social networks or recommendation engines. Think of nodes as entities and edges as relationships between them. They shine when analyzing complex relationships, something traditional databases struggle with.
This is fascinating. It's amazing how different models are optimized for different types of data and tasks. Now let's shift gears a bit and explore what happens inside the database engine itself, storage and retrieval. From what I've gathered, logs seem to play a crucial role.
Indeed, logs are surprisingly powerful. They're essentially append-only files that record every change made to the database. Think of them as a chronological journal. And they're incredibly efficient for writes because appending to a file is a very fast operation.
So it's like a constant stream of updates being added to a file. But how do you quickly find the information you need amidst all those entries? I mean, scrolling through a massive log file doesn't sound very efficient.
That's where indexes come in. They're the secret sauce for fast reads. Imagine searching through a phone book without an alphabetical index. It would take forever. Indexes are like signposts that guide you directly to the information you need without scanning the entire data set.
It's incredible how indexes can make searching through billions of records as easy as finding a book in a library.
Right. B-trees, for example, are incredibly efficient for looking up data quickly, even as the dataset grows. They automatically rebalance themselves to maintain performance, even when you're adding or removing lots of data.
Okay, that makes sense. But there are other types of indexes too, right? What about those SS stables and LSM trees I came across in the research?
Those are more specialized index structures, often used in those NoSQL databases we talked about, like Cassandra and LevelDB. They combine the efficiency of logs for writes with the sorted structure of B-trees for reads. It's a clever way to achieve both fast writes and fast reads.
It's mind-blowing how much thought goes into these seemingly simple operations. And we haven't even touched on full-text search indexes or in-memory databases. But I'm curious, how do these different storage engines handle the vast differences between, say, processing online transactions and analyzing huge data sets in a data warehouse?
That's a great question. OLTP systems, which handle online transactions, are all about speed. They need to be able to process small amounts of data very quickly, like when you're making a purchase online. Data warehouses, on the other hand, are designed for analyzing massive data sets.
So they have different needs and therefore require different tools.
Precisely. Data warehouses often employ column-oriented storage, which is excellent for compression and processing large volumes of data efficiently. Instead of storing data row by row, they store it column by column, making it much faster to analyze specific data points across a vast data set.
So it's like having all the ingredients for a specific recipe readily available instead of searching through the entire pantry every time. Makes perfect sense.
Exactly. And this approach also lends itself well to vectorized processing, allowing CPUs to analyze chunks of compressed data much faster than processing each record individually.
Okay, my mind is officially blown. It's incredible how much ingenuity goes into these systems to handle the massive amounts of data we generate daily. But speaking of data, let's move on to encoding and evolution, the art of data serialization. I'm sensing another deep dive coming on.
You're absolutely right. This is where we look at how we transform those complex data structures into byte sequences that can be stored or transmitted efficiently. And it's not as straightforward as it might seem, especially when you consider schema evolution, how these systems adapt as applications change over time.
Right, because applications are constantly evolving and the data they handle needs to evolve with them. I'm guessing this can get pretty tricky.
You're not wrong. Just think of all the software updates you install on your phone or computer. Those updates often involve changes to the underlying data structures, and we need a way to ensure that older data can still be read and processed by the updated applications.
So it's like when you update an app on your phone and the app still works with your old data. That's schema evolution in action, right?
Yeah, exactly. Some programming languages offer built-in encoding mechanisms, but they can be limiting. That's where schema-driven formats like Thrift, protocol buffers, and Avro come in. They provide a structured way to define the data format and handle those inevitable changes.
So it's like having a blueprint for your data that can be updated without demolishing the entire structure.
Precisely. Thrift and protocol buffers are great for compact encoding and maintaining compatibility with older versions. They use field tags to identify data elements, making it easy to add or remove fields without breaking existing code.
And what about Avro? Is it similar?
Avro is particularly interesting because it excels at handling schema evolution in databases. It doesn't enforce a strict schema, allowing for more flexibility when dealing with evolving data structures.
So it's like having a more adaptable blueprint that can accommodate changes more easily.
Exactly. And this is crucial for databases where schemas are constantly being modified to meet new requirements. But remember, these encodings are used in various systems, not just databases. They're essential for data flow in RPC and message passing systems, which rely on efficient communication between processes.
Right, like those behind-the-scenes communications that make online services work. What about message brokers? Where do they fit in?
Message brokers act as intermediaries in these systems, providing temporary storage and enabling asynchronous processing. They help manage the flow of data and ensure smooth communication even when systems are busy. It's like having a postal service that handles the delivery of messages between different parts of the system.
Okay, we've covered a lot of ground here, from the fundamentals of data systems to the intricate details of storage, retrieval, and encoding. It's truly amazing how much is happening behind the scenes to make our digital world function smoothly. But now comes the big question. How do we keep all this data safe and available? I'm talking about replication, the art of keeping data safe from those inevitable failures.
And that, my friend, is the perfect segue into our next chapter. Replication is all about creating multiple copies of data to ensure availability and protect against data loss. But as you'll see, there's a surprising amount of complexity involved. Replication is really all about making sure our data is safe and always accessible even when things go wrong. But as you mentioned, it's not just about copying files, is it?
Definitely not. I was reading about this thing called leader-based replication, and at first it sounded pretty simple. You have a leader, you have some followers, and the followers just copy what the leader does. But then I started digging into the details, and I came across all these terms like synchronous versus asynchronous replication, and then there's this whole thing about split brain scenarios, and things got a bit more complicated in my head.
It is a bit more complex than just copying and pasting. But you're right, leader-based replication is a very common approach, especially in relational databases and some NoSQL systems as well. Basically, you have one designated leader that accepts all the right operations.
So all the changes go to the leader first.
Exactly. And then the followers create copies of that data to keep everything in sync. But as you pointed out, the devil is in the details. For example, you have synchronous replication, where the leader waits for confirmation from all its followers before acknowledging a write.
So make sure everyone has the latest version before moving on.
Precisely. That ensures strong consistency, meaning everyone sees the same data at the same time. But the trade-off is that it can slow things down because the system is only as fast as its slowest follower.
Right, so it's that classic trade-off again, consistency versus speed. So what about asynchronous replication then? Is that the speed over accuracy approach?
Not quite inaccuracy, but it does mean accepting a higher tolerance for inconsistencies. With asynchronous replication, the leader doesn't wait for the followers to catch up. It acknowledges the write as soon as it's processed locally.
Okay, so it's a bit more of a gamble, but it's faster. What could go wrong?
Well, you do introduce the risk of data loss if the leader fails before the writes are replicated to the followers.
I see. So it's a trade-off between speed and the risk of losing data. Okay, now what about this whole split brain thing? It sounds kind of scary, like something out of a horror movie.
It's not quite that dramatic, but it can definitely cause some headaches. Imagine a scenario where there's a network interruption and the leader loses contact with its followers.
So they're all kind of isolated from each other.
Right. And the followers, not knowing what happened to the leader, might decide to elect a new leader amongst themselves.
Oh no, so now you have two leaders, both thinking they're in charge.
Exactly. And that's the split brain scenario. You now have two leaders, both potentially accepting rights, which could lead to conflicting data and all sorts of inconsistencies.
That sounds like a nightmare for developers. So how do you prevent that from happening?
There are various mechanisms in place to make sure only one leader is active at any given time. Think of it like a lock on a door. Only one person can hold the key and enter at a time.
Okay, that makes sense. So leader-based replication, while seemingly simple on the surface, has its fair share of complexities. But what about those other approaches I came across, like multi-leader and leaderless replication? When would you use those instead of the single-leader model?
Great question. Multi-leader replication is particularly useful in situations where you have multiple data centers, each needing to operate independently. For example, if you have a global service with users all over the world.
Right, so you might have a data center in Europe, one in Asia, and one in the US, all handling users in their respective regions.
Exactly. And in those cases, you might want each data center to have its own leader, accepting rights, and then replicating those changes to the leaders in other data centers.
So each data center is kind of like its own little kingdom.
In a way, yes. It allows for greater flexibility and resilience because each data center can operate independently, even if the connection to other data centers is disrupted. But it also introduces new challenges, especially when it comes to handling conflicting rights.
Right, because if you have multiple leaders accepting rights, there's a chance they might make different changes to the same data. How do you deal with that?
Conflict resolution becomes a crucial aspect of multi-leader replication. Systems need to be able to detect these conflicts and have mechanisms in place to reconcile them. Sometimes this involves custom logic developed by the application developers to determine which change should prevail.
So it can get quite complex. What about leaderless replication then? Is that even more chaotic?
Not necessarily. Leaderless replication is a different approach, popularized by systems like Amazon Dynamo and Apache Cassandra. It's designed for high availability and fault tolerance. In this model, clients write to multiple replicas directly, and reads also involve querying multiple replicas.
So there's no single leader calling the shots. It's more of a distributed approach.
Exactly. It spreads the responsibility across multiple nodes, making the system more resilient to failures. But how do you ensure that all these replicas eventually agree on the same data? Well, these systems rely on concepts like quorum and eventual consistency.
I've heard those terms before, but I'm not sure I fully understand them.
A quorum ensures that a certain number of replicas must agree on a write before it's considered successful. It's like taking a vote. The change is only accepted if enough replicas vote in favor of it. And eventual consistency means that replicas might temporarily hold different versions of the data, but they will eventually converge to a consistent state.
Okay, so it's a bit more relaxed on consistency, but it's designed to keep the system running smoothly, even if some nodes are down.
Exactly. And to help resolve any inconsistencies, Leaderless systems often employ mechanisms like read repair and anti-entropy to detect and reconcile discrepancies between replicas. It's all about making sure everyone is on the same page eventually.
It's fascinating how these different replication approaches tackle the fundamental challenges of data systems. But replicating data is just one part of the puzzle, right? What about dealing with those massive data sets we talked about earlier? How do you even begin to handle that kind of volume?
That brings us to the crucial concept of partitioning. Partitioning is all about scaling out data horizontally by dividing it into smaller chunks that can be distributed across multiple machines.
Okay, so it's like slicing a giant pizza so everyone can have a piece. But how do you decide how to slice it? Or in this case, how to partition the data?
There are two main approaches: key range partitioning and hash partitioning. In key range partitioning, the data is sorted by a specific key, and each partition owns a range of those keys. This works well for range queries, where you want to retrieve data within a specific range.
So if I want to find all users whose usernames start with the letter A, I'd know exactly which partition to look in.
Precisely. But key range partitioning can lead to hotspots where certain key ranges are accessed more frequently than others, causing an imbalance in the load distribution across partitions.
Ah, so you might end up with one machine working much harder than the others.
Exactly. That's where hash partitioning comes in.
Yeah.
In this approach, a hash function is applied to each key, randomly assigning keys to partitions.
So it's like shuffling the data randomly across different machines.
Precisely. This helps to distribute the data more evenly, reducing the risk of hotspots, but it comes with the trade-off that range queries become less efficient because the data is no longer sorted by key.
So it's another trade-off: order versus even distribution. It's amazing how all these seemingly simple choices have such a big impact on the system's performance.
Absolutely. And it doesn't end there. Secondary indexes also need to be partitioned, adding another layer of complexity. And then there's the question of how requests are routed to the correct partition. Some systems use a separate routing tier to handle this, while others rely on mechanisms like gossip protocols to disseminate information about partition locations.
Wow, it's like a sophisticated traffic management system for data. Okay, we've covered a lot of ground with replication and partitioning, but there's another crucial aspect of data systems that we haven't talked about yet: transactions. And I have a feeling this is where things get even more interesting.
You're absolutely right. Transactions are all about ensuring data consistency. Even when multiple operations are happening concurrently, they're like atomic units of work. Either all the operations within a transaction succeed, or they all fail. Transactions are all about making sure our data stays consistent even when there are multiple things happening at the same time. Think of them as like these little self-contained units of work.
So it's like either everything happens perfectly or nothing happens at all.
Exactly. Like when you transfer money between bank accounts, you want both the debit and credit to go through, or neither.
Right. Otherwise, you could end up with money just disappearing or appearing out of thin air.
And that's what transactions help prevent. They ensure that even if there are multiple operations happening concurrently, they're treated as a single unit and either all succeed or all fail.
Okay, that makes sense. But how do they actually work? How do these systems handle all these simultaneous operations without creating chaos?
Well, it's all about managing concurrency. A fancy way of saying how we deal with multiple things happening at the same time. We use something called concurrency control, which is a set of techniques to manage how transactions interact with each other.
So it's like having a traffic cop directing all the different operations, making sure they don't collide.
Exactly. A good analogy.
Yeah.
One of the key concepts here is isolation levels. They define the degree to which transactions can interfere with each other when they're happening at the same time.
So like different levels of separation to prevent them from messing each other up?
Exactly. There's a range of isolation levels from very strict to more relaxed. The strictest level is called serializable isolation. It guarantees that transactions behave as if they happen one after another in a specific order, preventing any inconsistencies.
So it's like a single lane road where only one car can pass at a time.
Exactly. It ensures perfect order, but it can slow things down significantly. Other isolation levels, like read committed, are more relaxed. They allow for some concurrency, but with weaker guarantees. They might prevent some problems, but they can still be susceptible to things like lost updates or write skew.
Right. So it's a trade-off again. Stronger guarantees often come at the cost of performance.
Precisely. You have to choose the right isolation level based on the specific needs of your application. But even with these isolation levels, ensuring consistency in a distributed system can be tricky.
because you have multiple machines involved and things can go wrong in so many different ways.
Exactly. And that brings us back to the chaos of distributed systems.
Right. All those things we talked about earlier, like network failures and unreliable clocks, they can really make things difficult.
They can. You have to design your systems with the assumption that things will go wrong at some point. It's not a matter of if, but when.
So you can't just assume that everything will always work perfectly.
Definitely not. You have to be prepared for all sorts of failures, from network interruptions to entire servers crashing.
So how do you design for that kind of unpredictability? Where do you even start?
Well, you start by acknowledging the inherent unreliability of the network. The network is the backbone of any distributed system, but it's also prone to all sorts of issues like latency packet loss and even complete outages.
Right, like when your internet goes down and you can't even load a web page.
Exactly.
Yeah.
In a distributed system, those network hiccups can cause all sorts of problems because nodes are constantly communicating with each other and relying on timely responses.
It's like trying to have a conversation with someone over a bad phone connection. You never know if they heard what you said or if their response is delayed because of a bad signal.
A great analogy.
Yeah.
And then you have the issue of unreliable clocks.
Right, because each machine has its own internal clock and they're never perfectly synchronized.
Exactly. And even the tiny discrepancies in those clocks can lead to all sorts of weird behavior, especially in systems that rely on precise timing.
So it's not just about the data itself, it's also about the order in which things happen and making sure that order is consistent across all the machines.
Precisely. And don't forget about process pauses. Things like garbage collection or virtual machine migrations can cause a process to pause for a moment, which might seem insignificant, but it can have ripple effects throughout the system.
It's like that annoying buffering symbol when you're streaming a video. It's a small interruption, but it can really disrupt the flow.
So how do you deal with all this unreliability? Well, there are a number of techniques that developers use. One common approach is to use timeouts and retries. If a node doesn't respond within a certain amount of time, you assume it's unavailable and try again later.
Okay, that makes sense. But what if the node is just slow and not actually down?
That's the tricky part. You have to carefully tune those timeouts to find a balance between responsiveness and avoiding unnecessary retries.
I can see how that would be a challenge.
And that's why idempotency is so important. It means that an operation can be executed multiple times without changing the result.
So it's like pressing the elevator button multiple times. It doesn't make the elevator come any faster.
Exactly. And in a distributed system where messages can get duplicated or operations can be retried, idempotency helps to prevent unintended consequences.
Okay, so timeouts, retries, and idempotency all help to make these systems more resilient. But what about those big concepts we hear all the time, like consistency and consensus? How do those fit into the picture?
They're absolutely crucial for ensuring that the system behaves predictably, even in the face of all this chaos. Consistency is about guarantees regarding the order in which writes are observed by different nodes.
So it's about making sure that everyone sees the same data in the same order, even if there are multiple copies of that data spread across different machines.
Exactly. And there are different levels of consistency. The strongest level is called linearizability. It basically means that all operations appear to happen instantly and in a specific order, as if there were only one copy of the data.
So it's like having a single authoritative source of truth?
Precisely. But achieving linearizability in a distributed system is really difficult and often comes at a high cost in terms of performance. So in practice, most systems rely on weaker consistency models that allow for some temporary inconsistencies between replicas.
So it's another one of those trade-offs between strong guarantees and performance.
Exactly. And then there's consensus, which is about getting multiple nodes to agree on something, even if there are failures.
That sounds really challenging, given all the potential for things to go wrong.
It is, but it's a fundamental building block for a lot of important tasks, like leader election distributed locking, and ensuring that all replicas eventually converge on the same state.
So it's like trying to get a group of people to agree on something, even if some of them are unavailable or have different opinions.
Exactly. And there are some really clever algorithms like Paxos and Raft that have been developed specifically for solving this consensus problem.
It's amazing how much thought and ingenuity has gone into making these systems work reliably despite all the challenges.
It really is. And as we generate more and more data, these challenges are only going to become more complex and more important to solve.
Absolutely. Well, this has been an incredible deep dive. We've covered so much ground, from the fundamentals of data systems to the intricate details of replication partitioning transactions and the chaos of distributed systems. It's clear that these systems are essential to our digital lives, and they require a remarkable amount of ingenuity to function reliably and efficiently.
It's been a pleasure exploring this world with you, and I hope our listeners have gained a new appreciation for the hidden complexity behind the apps and services they use every day.
I think they definitely have. So the next time you're browsing the web or using your favorite app, take a moment to appreciate the intricate dance of data happening behind the scenes. It's a world of constant innovation where developers are pushing the boundaries of what's possible with data. But it's also important to remember that these systems are not just about technology. They're also about people and the impact they have on our lives.
Well said. As we continue to generate more and more data, it's crucial that we use these powerful tools responsibly and ethically, with a focus on values like privacy, security, and fairness.
Absolutely. Well, that's all the time we have for today's deep dive. Thanks for joining us, and we'll see you next time for another exploration of the world's most fascinating topics.